Hi, welcome to session 15 for mentoring for a career in machine learning. In this session, we'll discuss about the problem of overfitting versus underfitting. This is one of the most important concepts because it helps us choose the right model which does not overfit the data, nor underfit and not able to explain the data. So once we have built a decision tree in the previous session, we will look at how to find the optimal depth of the tree, which does not underfit or does not overfit. So let's dive in. So I have uploaded a notebook under session 15 here called Understanding Overfitting and Underfitting. And we'll be using the same HR attrition data set to explore this particular concept. So let's start the notebook. We have already gone through the data set, so we'll not be spending much time in understanding the data set. So this is HR attrition data, and we have explored there's a variable called left, 0 if the employee did not leave, 1 if the employee left. And there are different variables like satisfaction level, last evaluation, we can use to predict it. So let's build a decision tree first. You have not gone through the previous sessions. So you can go through the previous sessions to understand about the data set and exploration of different variables and learn how to build a decision tree. So let's import all the required libraries, load the data. And we have about 14,999 data points here. And the first thing that we'll do is encode categorical features. So these two features we have, department and salary, as a categorical feature. So we're going to first encode them. And we will use we'll build a decision tree for classification. We will first list all the features. So all the columns in the data set, besides the column called left, which is your target variable, the left. 1 is the employee has left, 0 means the employee have not left. And the remaining ones, X features, which contains the features as they are, the numerical features, and the newly one-hot encoded features from these two categorical features, department and salary. So let's first set an X and Y values. So X would be all the X features and Y will be the variable left. And we'll first split the data into 80 and 20 ratio. So 11,999 samples in train, 3,000 samples in the test data, and build a decision tree classifier. Now, if you build a decision tree classifier, there are two hyperparameters, as you already discussed in the previous session. One is the criteria to search for the decision boundaries. One is Gini, and the other one is entropy. One is Gini, the other one is entropy. So either you can use any of these two. And the maximum depth, the depth of the tree. So this can be 1 depth or 2 depths or many depths. But first, let's build a simple model with just 1 depth of 1, and fit a model, X train and Y train, fit the model to the data. And if you measure the accuracy, let's look at ROC AUC. We'll predict from the train data and look at the ROC AUC, and it looks it's a 0.78. If you remember in the session 14, when we built a decision tree, the accuracy was about ROC AUC was 98%, 0.98. But we build that model with a depth of 5, but here we are actually using only depth of 1, just one node, the first node. And we can measure the accuracy on the train and test data. So when you build a model, what you can do is, when you split the data into train and test, when you build a model, you can measure the accuracy on the train data itself. You can apply the model to the train data, only the X features of the train data you provide, and then ask it to predict the Y value and compare with the Y train. And then you can also apply to the test data. You can provide the X values of the test data and ask it to predict the Y values, and then compare the accuracy, what accuracy you see on the training data and what accuracy you see in the test data. You can compare that. So in this case, on the train data 0.78 and on the test data 0.77, which is fine. There's not much of a difference. But if we increase the number of depth, for example, if you go back and rebuild the model with, let's say, depth 2, right, and you will fit the tree again. So in this case, we are using a depth of 2. And if you measure the accuracy here, you can see the accuracy has increased now to 0.90, right? So what we'll do is, then what is the most optimal depth? If we keep on increasing the depth, what happens? We'll go and verify that. So checking the underfitting and overfitting. So in this case, if you see, if we had built the tree with only a depth of 1, right, it was giving an accuracy of 0.78 ROC AOC, and the depth of 2, it is increased to 0.90. So definitely the depth of 1 is an underfitting model. It does not fit to the data. If you little bit increase the depth, it will fit to the data more, right? But if we keep on increasing, what happens? We need to observe that. So there are two conditions here. One is underfitting and one is overfitting. So what is underfitting? Underfitting occurs when a machine learning model is too simple. For example, in our case, we can relate it to building a tree with a depth of 1 and lacks the capacity to capture the underlying pattern on the data. We saw that, and this is, of course, you can observe with measuring the accuracy of the model. And it fails to learn the relevant relationship between the features and the target variable, resulting in poor performance. We saw that. And both on training and test data, we saw that it was giving a accuracy of 0.78 on the train and test. But what is overfitting is, overfitting a model tends to have a very high accuracy on the training data. So what happens is, if we, in this case, we, of course, we saw the train and test accuracy both are same. But if we, what will happen is, if we start building a model with more depth, 3, 4, 5, 6, what will happen is this training error, training accuracy will keep on increasing. It will become better and better. But a test accuracy will not increase over a period of time. Beyond certain depth, the test accuracy will remain stable or constant, or will start diminishing. So that is basically called the condition of overfitting. An overfit model tends to have a very high accuracy on the training data, since it has effectively memorized the training example. Because if you keep on learning and keep the model very complex, it'll almost like memorize all the training data patterns. But the whole idea of building a model is to generalize, right? Is to generalize. So it will not learn the necessary pattern. It will also learn some of the very, very local patterns on the training data, which won't be relevant for predicting on the test data. However, if you see here, when evaluated on the test data, the performance drops significantly due to its inability to generalize well. This is a very, very important term here. But can we simulate this and see that? So what we'll do is here, we'll create a train accuracy list here and a test accuracy list here. And we'll iterate through many depths, starting from the depth of 1 to depth of 20. And then what we'll go and build a decision tree classifier with that particular depth. So first we'll build a model with the depth of 1, the depth of 2, depth of 2, 3, and until depth of 20. And then fit a model, right? And once you fit a model, we'll predict the probabilities on the extreme and measure the accuracy, right? We'll measure the accuracy and append to the ROC score to the train accuracy, and also predict the probability on the test data and measure the ROC and append to the test accuracy. So we'll build model with depth 1, we'll measure the train accuracy, and we'll measure the test accuracy. Both will be the same accuracy, ROC, AUC in this case. So depth of 2, depth of 3, and CL. And then what we'll do is we'll observe the trend in that. So let's run this. Now, if you see, you have built a model depth 1, 2, 3, up to 19. And now we'll create data frame with a column called depth, which will store the depth that we use in the decision tree, the corresponding train accuracy, and the corresponding test accuracy. And if you look at the data frame here, as we increase the depth of the tree, you can see the train accuracy has gone from 0.78 to 0.90, then 96, then 97, 97, 98, and all that. And it's constantly increasing. And almost here it's increased to the level of 1.0. But here, if you see, the accuracy is of course increased, but then after some point of time, if you see here, the depth, the accuracy starts diminishing. Okay, it's not increasing along with the train accuracy. And if you plot this here, let's say line plot, depth versus train accuracy and depth versus test accuracy, both the line plots. And if you overlap it on each other, so this is a very, very important plot here. The x-axis shows the depth of the tree, which is also called the model complexity here. It's called the model complexity because the depth is 1, we can say very simple model. Depth is 19 or 20, it's called a very complex model. So as we increase the depth of the decision tree, we'll measure the accuracy on the y-axis, and the orange one represents the test and the blue one represents the train accuracy. So you can see here, when the depth was 1, both and train test accuracy is very low, less than 0.8. But as we increased the depth, the train accuracy improved and the test accuracy is also improved. Until, of course, till some point it increased significantly, very rapidly after started flattening it out. But at a particular point of time, for example, let's say a depth of 7 or something, if we increase the complexity further, the train accuracy is still increasing, though at a very small steps. But the test accuracy has started reducing and diminishing. Okay, so this is a very, very important graph, because if you see here, this is the region we call it an underfit, right? And this is where if you build a model less than this, the model is still not able to explain everything, and still something more there in the data to be learned. And this is the area of what we call it overfit, where we are learning something that's not necessary, or probably it's actually diminishing the quality of the model, because whatever you are learning is not relevant for the test data. In fact, is hampering the quality of the model. But here is the most optimal point here, if you see here. So if this is the model where to keep the model depth, the train accuracy and test accuracy is the highest. So if you see a difference between a train, so if you look at the train and test accuracy in this case, if both are low, right, then that's basically a classic case of underfit. But when the train accuracy is high and the test accuracy is low, that means basically there's a difference between these two. That's basically a case of what? Overfit. But when both are same, pretty much same, of course, it won't be exactly same. Maybe 1-2% is fine in some cases, depending on the data set size and the quality of the model. If both are high, then this is, of course, the most optimal thing that we are looking for. So in this case, I would say this is the most optimal part. So this is the depth that should be chosen to build the model. Now, how do I find the optimal complexity, the depth here in this case? Either you can do like this, but the most important part is we can use actually cross-validation, k-fold cross-validation for a very rigorous testing and such. So what we'll do is we'll build a decision tree. So let me go through a little in detail. So what you can do is you can take the data, the training data, and split it into multiple folds. Let's say we'll split the training data into 5 folds, like a K1, K2, K3, K4, and K5. We already have discussed in depth about cross-validation previously. If you're not watched, please go and watch that video. Now we'll build a decision tree with a depth of 1. And then what we'll do is we will cross-validate 5 times here. So we'll build a tree with a K1, K2, K3, K4, and test it against K5. Then K1, K3, K4, sorry, K2, K3, and K5, and test it against K4, and so on and so forth. And then we'll take an average of ROC, AUC of all this. So what you can do is you can say, we use a technique called grid search, which again we have discussed in one of the previous session. So from scikit-learn model selection grid search here, and we will search for both the parameters now, max depth and criteria. So depth can be varied from 1 to 20, and criteria can also be Gini or entropy. So combination of both, for example, depth is 1 and Gini, depth is 1 and entropy, depth is 2 Gini, depth is 2 entropy, so on and so forth until the depth of 20 Gini and entropy. Okay. In this case, of course, it'll go up to 19, but that's fine. So for each of these combinations, we'll build a decision tree and cross-validate and measure the cross-validation score. So we'll set that as a params. And then in the grid search CV, we initialize the decision tree classifier without any parameter and ask him to choose those, take those parameters, combinations from the params here. And then we'll say, do 10 times cross-validation for each of the combinations. And then scoring is ROC, AUC. And then we'll fit the train data to that. Now, if you fit the train data and it returns something called CV results. So here it would have already gone through all possible combinations and done a cross-validation. So now let's look at the CV results. I'm converting that into a grid search. It gives a lot of information, but I'm just limiting it to only this 5 pieces of information and sorting the values by the rank. I'll show what the rank is here. And if you see, it says that the entropy with 7 gives the best min test score is about 0.98. That's the best score, and it's ranked 1. and the standard deviation is also very less. Entropy with 6 gives the next best, and so on and so forth. So this is the best way to find the most optimal parameter. And it also gives the ranks automatically based on the highest mean test score here. So you can say finding the best param and best accuracy. It also returns to variables like best underscore param underscore, which tells you that entropy and 7 gives you the best score. The best score is 0.9820, which is same here. So either you can take it from the CV results, or you can specifically ask to return those best parameter and best score here. So in this particular session, we looked at what is underfitting and overfitting, how to measure the model complexity, and how to find the most optimal level of complexity so that the model does not underfit and does not overfit by doing a grid search through cross-validation. So the model complexity parameter could vary from model to model. For example, depth could be a complexity for decision tree, or for KNN, the number of neighbors is considered as the model complexity. If the number of neighbors is 1, 2, up to let's say 100, of course, this is a simple model, and this is a complex model. And somewhere in between, there is a optimal value for the number of neighbors. So as an exercise, I will leave it to you to build a KNN classifier for this HR attrition problem, and use only the 5 important features specified here: satisfaction level, last evaluation, number of projects, average monthly hours, time spent in the company. And here n neighbors, number of neighbors is a hyperparameter and is a factor of complexity for the KNN model here. So build a model with n neighbors varying from 2 to 20, then measure, train, and test accuracy against n neighbors. And you can also draw this plot, both train and test accuracy against the number of neighbors, and see which is the optimal value. And you can also do using grid search cross validation. So thank you for watching this, and I'll see you next week with a new topic.